Okay, awesome. So there we go. Now, last time we were discussing about redundant array of inexpensive disks, or RAID. Sometimes, this is also called as redundant array of independent disks. The terminology doesn't matter, the concepts are the same. And we were going to look at different RAID levels, RAID 0 through 5, and see what the differences were, what the trade-offs were in terms of both the performance and reliability. Okay, so that's what we're going to do now. So we had looked at RAID 0 earlier, and the idea there was that we would take a data block, the array of blocks from the logical address space, and then stripe them across all the disks. So in this example, block 0 through 3 would go across all the disks, and then block 4 through 7, and so on, right? So by doing this, we can exploit greater parallelism because multiple I/O operations can be issued at the same time to different disks, and so that way you can increase the throughput. The disadvantage here was that if any of these disks fail, then we end up with the complete loss of data. So we get great throughput, but terrible reliability. Also, another thing that we discussed last time was that the reliability of the entire disk array is worse than that of a single disk, right? Because now there is greater chance that any of these single disks can fail. So, so at any given time, you have to worry about one of the 4 disks failing versus just one disk. So we want to get better reliability, and a simple way to get reliability is to make a backup copy, right? So so here we talked about RAID 1, which was where we had made a backup. We had backup disks for every primary disk. So for every write operation, we would write to 2 disks. So disk 0 data would be written to mirror 0, and then disk 1 data would be written to mirror 1. So, and these operations have to be atomic, like someone asked last time, in the sense that you can't consider a write operation to be complete unless data is written to both the disks. Okay, so so by doing this, we get better reliability. If any one disk fails, we can recover it from the other disk. And for certain 2 disk failure scenarios, we can recover from those as well. For example, if disk 0 and disk 1 fail, then we can restore them both from mirror 0 and mirror 1. Or if disk 1 and mirror 0 fail, then we can restore them from the corresponding other disks, right? So there are many 2 disk failure scenarios this can handle. Only thing that it can't handle is if the primary disk and the mirror disk both fail at the same time, or before you can recover the first failed disk. So in this case, these 2 disk scenarios we can't recover. Okay, so RAID 1 is pretty good in terms of both reliability and throughput. You can the more disks you have, the more parallel I/O operations you can perform at the same time. So so it's great in terms of throughput also, but in terms of capacity or usage of the disk space, it's terrible because we are keeping redundant copies of the same data. So we are wasting half the disk storage capacity. So we briefly discussed RAID 2, which was meant to address that problem, which was that you didn't want to set aside half the capacity. Instead, we want to compute some checksum or parity information. And then that parity information could tell us whether there is any error in the data and how to recover from it. So the more the bits we have for parity information, the better is your error correction chances, right? So there is a whole theory behind error detection and error correction from information theory, signal theory, and we can apply those here, right? But this was mainly useful for the old disks where error detection was not built in into the disks. these days, most of the disks that we buy, they have some form of error detection built in, which means that if a block gets into error, there are some error correction codes that are stored, and then the disk firmware can automatically recover the failed data up to some extent. Okay. Well, it's only when the disk completely fails in an unrecoverable manner that's when we need um, to handle the disk failure at software level, right? Or at the RAID controller level. So RAID 2 is not used anymore because now there are simpler mechanisms possible, since disk hardware itself comes with error detection mechanism. Okay, so we only need to worry about the case where the entire disk fails. Okay, any questions so far? All right, so we also looked at this truth table that we'll be using for the rest of the RAID levels. Here, the idea was that we're going to use this XOR operation to compute something called parity. So what this means is that if we have 2 bits of information, if we do an XOR, then the resulting bit can serve as a parity information or a checksum information. So, so this parity information is associative and commutative. So what that means is that, you know, if you have say more than 2 bits that you're doing an XOR operation, doesn't matter what order you do the XOR operation, the result would be the same. That's associativity. Then commutativity means that you can take the left-hand side, part of the left-hand side to the right-hand side, and the equation will still hold. All right. So this is very useful, as we will see. So now, if you have any one of these bits of information lost, then because of this associativity and commutativity properties, we can recompute the lost bit by simply doing an XOR of the remaining pieces of data. Okay, so this is also interesting in the sense that it doesn't matter how many bits you have on the left-hand side. For example, here we have 3 bits, and then there's only 1 parity bit, right? Even if we had like 4 bits or 5 bits or 6 bits, we would still need only 1 parity bit, right? Because the result of XOR operation is just, you know, 1 bit. So, which is very nice because our parity overhead does not increase with the number of bits of information that we are doing an XOR over, right? So, so what we just discussed for 1 bit, we are going to generalize it to entire blocks of data, and then we're going to see how RAID can be used with block level XOR operation. Is that clear? Any questions you have about how this parity computation works? Okay, so let's get going to RAID number 3. All right, so RAID number 3 is an improvement over both, you know, RAID 1 and RAID 2. So the idea here is that we will take a single block of data and we will chop it up into multiple fragments. All right. So in RAID 3, one of the things we will see is that there are n plus 1 disk drives. So what that means is n is the number of disks on which data will be stored, and plus 1 disk is for storing the parity information. So for example, in this picture, we have disk 0, 1, and 2, in which we store the data. And then disk 3 is where we store the parity information. Okay. Now, the way RAID 3 would work, RAID 3 is one of the simpler cases where the RAID controller works on only 1 block at a time. So it does not offer any read-write parallelism across block level. Okay, so for example, take block 0. All right, so we take block 0, and then since we have 3 data disks, we divide it into 3 parts: block 01, block 02, block 03. Okay, and then we divide these 3 fragments of block 0 on 3 different disks: disk 0, disk 1, and disk 2. All right, so now when we do this, then we will compute a parity of all these 3 blocks together. We'll do an XOR operation of block 01, 02, and 03, and that will become parity 0. Okay, so when we say we are doing an XOR operation across these fragments, what we're doing is we're taking corresponding bits of each block and doing an XOR. So bit 0 of each of these fragments would result in bit 0 of parity, right? So bit 1 of each of these fragments would result in bit 1 of parity, and so on. All right, so we do this 1 block at a time. So likewise, block 1 gets chopped up among 3 blocks, and there's the parity. So this is, so now if we lose any single disk, then we can recover that lost disk by doing a parity of the remaining disks, the blocks and the fragments in the remaining disk. So for example, if we lose, let's say this block 1, 2, right? So in order to recover block 1, 2, let's say we lose disk 1, like since we're talking about disk level fault tolerance. So if we lose the entire disk 1, we can recover all these blocks by doing an XOR of the remaining fragments in the rest of the disks. So for example, to recover block 1, 2, we would do an XOR of block 1, 1 and block 1, 3 and parity 1. So when we do that, we will get back our block 1, 2. So as long as only one disk has failed at any time, we can get that failed disk back by doing an XOR of the remaining contents of the remaining disks. Okay, so all these complex equations that you see on the slide, they are basically encapsulating the same thing. So if you had lost disk I, if you had lost disk K, for example, let me see. Sorry, yeah, if you had lost disk I, for example, then the way you would recompute the rest of the contents would be doing an XOR of the fragments of the remaining disks. Okay. All right. So any questions so far? You guys are really quiet, so I'm really not sure if anyone is understanding. And I can, usually in a classroom, I can see heads nodding, right? And I can't see your heads nodding anymore. So, all right, we'll try to make the best of this situation. Okay. What is the, okay, great, first question. What is the advantage of fragmenting the data like this? Okay, yeah, that's a very good question. So it kind of feels weird, right? So you're taking a block and chopping it up. Like, why don't we keep the block together? So this is just for, surprisingly, it's for implementation simplicity. So earlier, suppose you don't want to spend a lot of money on a complex RAID controller that handles a lot of IO requests. So you have a simple RAID controller that just handles one IO request at a time. Okay, you give it a block, it will finish doing an IO operation on that block, and then it will come back to you and get the next block. Okay, so if you have such a simple logic built into the RAID controller hardware, then you can use something like RAID 3. Okay, you get some very limited parallelism in the sense that multiple pieces of a single block can be read or written simultaneously, but you also don't, it's not much of it, because in order to compute the parity, you need to like do that operation over all the blocks and then write to the parity disk. So there is intra-block parallelism, but no inter-block parallelism, right? There's no parallelism across different blocks. So it's mainly implementation simplicity, right? In practice, you would not see people using RAID 3 if they want throughput. Okay, if you really want performance improvement, then you don't want to be using RAID 3. Okay, in that case, RAID 1 or even RAID 0 will be a better option. Or you could go for RAID 5 that we will discuss next. Does that answer? Okay. Any other questions? All right. So we're going to next look at RAID 4. So here again, the problem that we identified with RAID 3 is that, okay, oh, there's one more question, but this was sent privately. So I'm gonna, so yeah, it would be great if you can send your messages to the whole class so everyone knows. So I'm gonna copy and paste the question for the whole class from Jasmeet Kaur. He's asking, if we lose more than one disk, we cannot recover in this also. So what is the advantage of RAID 3 over RAID 2? Okay, so again, that's a great question. So the question is, if we lose any disk, in this case, more than one disk before we can recover the first one, then we lost everything, right? So what's the advantage? So in all these RAID models that we are discussing, our failure recovery model is that we want to recover from a single disk failure. Okay, we are not aiming to recover from two disk failure. So we want to guarantee that we can recover from any single disk failure. Okay, so in terms of the number of disks from which we can recover, whose failure we can recover, none of these models are better than the other. Actually, if you think about it, RAID 1 is slightly better than RAID 3 because RAID 1 can recover from some two disk failures, actually most two disk failures. Or in RAID 1, if the primary and the backup fail, then you can't recover from that. But other than that, you can recover from any two disk failure. In the other models we're discussing, 2, 3, 4, and 5, you can't recover from any two disk failure. Okay, so because the parity computation depends upon having all the disks, and recovering a lost disk here now requires that all the other disks be uncorrupted, right? So, so as to what is the advantage of RAID 3 over RAID 2 here, it's simply that you don't have to do error detection. In RAID 2, we had to do error detection, right? But in RAID 3, we don't have to do error detection. The disk itself provides you error detection, so we can focus on error correction. Once the disk says I have failed, then you can replace it and reconstruct it. So we focus on error correction. So, all right. Does that make sense? Any questions? Okay, so let's go to the next one. All right, so now we want to increase the parallelism. So the RAID 3 can only handle one IO operation at a time, one block at a time, one read or one write operation at a time. So, so in order to improve parallelism, what we can do is that we can keep a block together, right? So now we are willing to spend more money to buy a RAID controller that can handle multiple blocks in parallel. So so now that brings us to RAID 4. Okay, so RAID 4 is very similar to RAID 0 that we discussed earlier, except that there is one parity disk. So again, just like RAID 3, we have n+1 disks. There are n data disks and one parity disk. All right, and now we don't chop off a block into smaller fragments. We keep a block together. So there is a block that comes from IO operation. It goes on a single disk, right? When block 1 comes in, it goes on disk 1. Block 2, the whole block goes on disk 2, and so on. So we are striping across the disks just like we did with RAID 0 and RAID 1 for that matter. Okay, but unlike RAID 1, in RAID 1 we were keeping a mirror backup copy, but instead now we are going to compute a parity across the blocks in the same row and store the corresponding parity in the parity disk. Okay, so so likewise block 3, 4, and 5 would make parity 1 and so on. All right, So by doing this, now we can do read and write operation to different disks independent of each other, and we can increase the effective parallelism. For example, I could be reading block 3 and block 7 and block 5 simultaneously, and that way I can get n times more parallelism than in the previous case, and then in RAID 3. Okay, so that's what these equations are doing. And similarly, if any disk fails, we can recover the failed data by doing an XOR of the remaining disks, just like what we did in the previous case. So this seems fairly simple, but there is always a catch, all right? And the catch is for write operations. And at the first sight, it may look like we can write to all the disks in parallel. Okay, so you can say, hey, I can write to block 0 and block 4 and block 2 or block 8, at the same time, but not so fast, because when you write a block, right, the parity information has to be updated. Okay, so for example, if I'm writing to block 0 and block 4 at the same time, right, so parity 0 would have to be updated and parity 1 would have to be updated. Now, what happens, because parity disk is a single disk, all the IO operations going to the parity disk are sequential, one behind the other, right? So you may have to write parity 0 first, then parity 1. So what we're doing is, although it may look like block 0 and 4 are written in parallel, but actually the parity information has been serialized, so effectively you're only doing one IO operation at a time. Okay, so your IO operation is not complete till the parity information is committed into the parity disk. Before that, the disk array cannot signal to the OS that the IO operation is complete, the write operation is complete. So unfortunately, because the parity disk is a bottleneck, therefore, this does not provide any write parallelism. Okay, so write operations are still sequential. So you can get read parallelism, but no write parallelism. All right, does it make sense? Any questions on this? Okay, let's see. If anyone is raising their hands, I need to check. Okay. All right. So, okay, so if this is clear, then I would proceed to RAID 5. So we're going to solve this problem that the parity disk is a bottleneck. Okay, so if the parity disk is a bottleneck for write operations, then what we're going to do is we're going to spread it out across all the disks. So now RAID 5 is just like RAID 4, except for one difference, that there is no dedicated parity disk. You see that now there are 4 disks, but there's no disk dedicated as a parity disk. Instead, the parity blocks are spread out or staggered over all the disks. So for the first row, block 0, 1, and 2, parity 0 is on disk 3. For the second row, block 3, 4, and 5, parity 1 is on disk 2. Likewise, the next row, parity 2 is on disk 1 and parity 3 is on disk 0. Okay, so by doing this, by spreading out the parity, we are preventing any single disk from becoming a bottleneck. So for example, if we were writing to block 0 and block 4 at the same time, then we'd have to update parity 0 and parity 1. And well, parity 0 and 1 are on 2 different disks, so we can commit those write operations in parallel, right? So in this case, but still we'll be using at least 2 disks at the same time, right? So in this particular case, we would we would be having parallelism of 2, that is 4 by 2. All right, does that make sense? Okay. So instead of just performing one I operation earlier, now we'll be able to perform two I operations at the same time. Likewise, if you had like 8 disks, then you would be able to perform 4 I operations at the same time, 4 write operations at the same time. Okay, so read parallel, and you can notice that the read parallelism also goes up. So for example, I can be reading block 0, 1, 2, and 5 at the same time. So I can do 4 read operations at the same time rather than 3 in the previous case. Okay, so this RAID 5 is certainly better. Okay, um, so I just want to see if anyone has any questions on either RAID 4 or RAID 5, what we've discussed so far. And if anyone can find any mistake in what I have said so far. Okay, so the question is, can you explain how the parity part works again for RAID 5? Okay, sure. So in RAID 4, like we were taking the data blocks, block 0, 1, 2, right? And then we were doing an XOR of those blocks and writing it in parity 0, right? So, and then block 3, 4, 5, the corresponding XOR operation would result in parity 1. Okay, so we're doing the exact same thing, all right? So if you look at the comparison of these two pictures, let me shrink it a little bit there. So up there is RAID 4, this is RAID 5, okay? So you would notice that in the second row, the first row is exactly the same, parity 0 is on the last disk. But for the second row, block 3, block 4 are on the same disks, but block 5 is on the last disk. Okay, here block 5 was on disk 2, here it is on disk 3. Okay, so why did we do that? So that parity 1 could be on a different disk than parity 0. So parity 1 goes here. So what that means is we take an XOR of block 3, block 4, and block 5 and write it to parity 1. All right. We're doing the same operation as before, except that the parity is on a different disk. And likewise for the next row. Here in RAID 4, parity 2 was on the last disk. In RAID 5, parity 2 is on disk 1. So we stagger it. Does that make sense? Okay, great. So now, can anyone find a problem that, I guess you can always go to the next slide, but I'm going to assume you won't look into the next slide and see, what is the problem with writes? Okay, I just told you that writes are parallel. Can you tell me why that may not be the case, even with RAID 5 as I've described to you? And you can unmute yourself and speak if you want. Anybody wants to be brave? Okay, so I'll be more specific. That the claim is, even with all the, after staggering the parity like this, the writes are still not parallel. Okay, so the thing that I just said, you can get n by 2 parallelism in writes. You can do n by 2 writes in parallel. That's still not correct. So here's Harshit is answering, if the second write is performed on the disk containing the parity of the first write. Well, yeah, that's true. So he's saying, okay, suppose you were writing to block 0 and block 5. Okay, so that's of course a problem, because parity 0 and block 5, the writes would go to the same disk and they will be sequential. Okay, so yeah, those operations won't be parallel. Only if we're doing block 0 and block 4, or block 1 and block 3, right? or whatever combination where the parities are on actually different disks. So then you can get parallelism. But so the claim is not that you always get n by 2 parallelism. The maximum parallelism you can get is n by 2. Okay, that's more accurate. But there's a more fundamental problem in this right operation. Okay, so okay, so there Anurag is saying, doesn't parity update operation make data writing delayed? Okay. Yeah, so you're saying parity update operation. So in order to update the parity, you have to recompute the parity and then you have to write it. Wouldn't it delay the data write operation? Yes, it would add some delay over typical write to a single disk, but we are hoping that whoever is implementing the rate controller, who is doing it in the hardware, these operations happen in the hardware, they do it fast enough that it wouldn't be significantly noticeable. Okay, so other than hardware latency issue, why would this not be parallel? And there is a hint there that parity update, like if you want to update the parity information. Okay, so there's an answer, because for disk 2 we cannot write in block 2 710 if parity 1 is being updated. For disk 2 we cannot write in blocks 2 7 and 10 if parity 1 is being updated. Yeah, of course, you can't do that. That's related to the previous answer by Harshit, right? That if you're updating a parity on a disk, you can't be parallelly writing to other blocks on the same disk. But then if your writes are such that their parities are also on different disks and their blocks are on different disks, then you can. Okay, so Satrio has a answer. Is it because we need the other blocks to compute a parity? The other blocks in the same row? Yep, there you go. So if you think about how parity is computed, so now that will take me to the next slide, right? So what is this right problem? So in order to compute the parity, you need all the other blocks in the same row. Okay, so so let's say that I am writing to block nk, then to recompute pk, I'm updating block nk, I have to recompute pk, but how do I recompute it? I have to take an XOR of all the other blocks. How do I do an XOR of all the other blocks? I have to read them and then recompute the new parity, and then I have to write the new block and write the new parity. Okay, so in order to compute the parity, if I do it in a naive way, okay, so that will take me to the next slide. So a naive way would be that I want to perform one write operation, okay? And what I would need to do is I would have to read all the other blocks from the other disks, recompute the parity, and then write the new block, and then write the new parity, okay? So this is the naive way. So this, if you do it the naive way, it will require n-1 reads. So why does it matter? Because we go back to this figure, what that says is that in order to update parity 0, I have to engage all the other disks. Okay, so if I'm reading from all those disks, I can't write anything to them. So like, for example, if I wanted to update block 4, but then I'm having to read block 1 to update parity 0. So I can't read block 4 until parity 0 is updated, right? If I do it the dumb way, then this would be the problem, that parity computation is still sequential, although the parity blocks are on different disks, but parity computation becomes still sequential. Okay, so we are not going to get the additional parallelism we want unless we solve this bottleneck. Okay, so what we want is we want to recompute the parity 0 or parity 1 or whatever. We want to recompute it without having to read all the other disks. Okay, So, so that the other disks are free to handle other I/O operations. So this naive solution, which requires n-1 reads and 2 writes, that's not going to work. Okay. I mean, it will work, but it won't give you the parallelism that you need. Does that make sense? Does anyone have any questions on why recomputing the parity by reading all the other blocks, why this is still sequential? Like anything in this discussion that didn't make sense so far? Okay, so I'm gonna assume that everyone is on the same page, and then we'll say how now we can recompute the parity without doing these n-1 reads on the without doing these n-1 reads. Okay. Now, the smarter solution is to recognize that the parity computation is commutative. Okay, commutative means that you can take some parts of the left-hand side to the right-hand side, and the resulting equation would still be valid. Okay, so let's say that we wanted to update a particular block of data, right? But remember that there were old blocks and the old parity information. There's new block and new parity information. So let me see how I can explain it better, because these equations can be a little confusing. So let me try to give an example of by writing things down. Okay, so I'm going to use this space in the middle. So let's say that, in the previous example, I'm just going to write this as, say, I had B0 XOR B1 XOR B2 equal to P. All right. So P was the parity block. Now, so I'm going to update one of these blocks. So let's say that I'm going to call this B0 old. All right. And this is parity old. So this was the original state of one of the rows there. Now, when I update this, so if I update B0, then this B old becomes B new, right? And the resulting P old becomes P new. Okay, so I have, let's see. So I have this, what do you call it? Change the color of the whole thing. Okay, anyway, so I have B new, all right, and I need to recompute P new. But what I don't want to do is I don't want to go to the disks and read B1 and B2. Okay, so I don't want to recompute this equation. If I were to go and read B1 and B2 from the disk, that would make the entire process sequential. So instead, what I'm going to do is go back to this original equation and see, how I can extract the value of B1 and B2, right? Because B1 and B2 have not changed, only B0 has changed. So what I can do is I can rewrite that first equation in a different way. I apologize for this online editing here, but hopefully this will make it more clear. So if I use the commutative property, I can say B1 XOR B2 equals P old equals P old XOR B old. Okay, would you agree with that? Yeah, does that make sense? How we can, great. Thank you for saying yes. And you can also say no if you did not understand. Uh, okay, so uh, so now that we have B1 XOR B2, we can take this value. Oops, let me write. We can take this B1 XOR B2 and plug it in here in this equation. So this part of the equation that we are trying to solve to compute P new. Okay, so by extension, I'm going to do a copy and paste. So if I just replace that part from the equation above, this becomes P old XOR B old, right? So as you can see, this brand new equation that we have here, this is completely based upon the values we know from two disks. It does not go and try to access the disks for B1 and B2, right? So we have the new value of B0, we have the old value of parity, we have the old value of the data block, and we just XOR them together, and then we can get the new parity, right? So we just by data from two disks, we can recompute the new parity, which is pretty cool, okay? So if you don't have to, even if there you had like, instead of 3, you had like 20 disks, it doesn't matter. You don't have to go and access the other 18 disks. You only have to access 2 disks, the one where the data is being updated and the one where the parity is being stored, okay? So it's very neat solution, right? And it all follows from the simple commutativity property that we discussed. So it doesn't matter how many disks you have in the array, there will be only 2 reads and 2 writes. Why 2 reads? Um, we have to read P old and B old, right? The old value of the data and the old value of the parity. And we already have the new value of the data, and we just recomputed the parity, and we just write B new and P new, 2 writes, okay? So by doing this, we can make sure that we don't access all the disks, and we can actually perform parallel writes. Okay, so going back to the original problem that we had, if we are now writing block 0 and block 4 in parallel, then for the first write, only disk 0 and disk 3 will be engaged, and for the second one, only disk 1 and disk 2 will be engaged. Okay, so which means those write operations can happen in parallel. Okay. And there is one more thing I want you to consider. Here I said, 2 writes and 2 reads, but you could have just 1 read if you're careful. Like, what that means is that usually when you write to a file, you have to first read that data block into the memory, into the operating system, right? And then you update some bytes in that data block, and then you write the block back. Okay, so one of the reads has already been performed. Like the read for this B old here, it was already done ahead of time by the OS. So that data is already there, and when the new data value is written back, you don't have to go and read B old again, because one read was already done. So only extra read you have to do is for P old. So by being a little more smart, you can reduce this to just 1 read and 2 writes. So it's not even 2 reads and 2 writes, just 1 read and 2 writes. Okay. Any questions on this? Does this make sense? Now, of course, the slide looks ugly, and I have to find out a way to edit the slide. I will edit the slide later and put that in, or you can also have it in the recording. Okay. All right, if there are no questions, we will proceed further. So here's a comparison of all the different schemes, and I won't go through each one of these, but they compare RAID 0 through 5 in terms of fault tolerance, maximum read parallelism, maximum write parallelism, and the space overhead. So how much extra space do you need beyond the data, all right? And you would notice that in terms of fault tolerance, RAID 0 has no fault tolerance. If you lose one disk, you lose all the data. RAID 1 can recover from at most one disk failure and most of the two disk failures. RAID 2 can recover from one disk failure with error detection and correction. RAID 3 can recover from one disk failure with error correction. So all the remaining ones can recover from only one disk failure. So it's interesting that RAID 2, 3, 4, and 5, although they are supposed to be higher RAID levels, but they don't necessarily offer better fault tolerance. They are actually just using the disk space more efficiently. Okay, so and in terms of reliability, RAID 3, 4, and 5 are not better than RAID 1. Okay, so RAID 1 is actually better than the others. And then if you look at the read parallel, how many simultaneous read operations you can do, most of these can do n. In RAID 5, if you consider the parity disk to be the additional disk, that's n plus 1. I think I should have written RAID 0 also n plus 1 in order to normalize them. RAID 3 can only do one IO operation at a time, whether reads or writes. Okay. In terms of write parallelism, again, RAID 1 allows you to do n by 2 write operations at a time, and RAID 5, again, n plus 1 or n by 2, depending on how you compute n. So, space overhead wise, that's where the rest of the RAID levels are better than RAID 1. You have 100% overhead for RAID 1, whereas 1 by n times 100% for the other RAID levels. Okay. So, any questions in any of this? So this is just like a summary of what we have discussed already, except with more formulas. Okay, so in conclusion for this chapter, so originally people thought of RAID because they wanted to put together lots of small disks to make a higher capacity disk. So this was one of the earliest forms of storage virtualization. But nowadays, capacity is not an issue. You can buy large disks, but then the speed of accessing data is very important, and reliability is important. So people want instantaneous backup. You don't want to like do a nightly backup, which will take like hours and hours to complete. So RAID can give you instantaneous fault tolerance, and high throughput. So parallelism is really important aspect. So, so typically people would go for either RAID 1 or RAID 3 or RAID 5. Nobody really uses RAID 2 or RAID 4 for that matter. And of course, this is just if you want to recover from a single disk failure. If you want to recover from multiple disk failure, there are higher RAID levels that we have not discussed here. For example, RAID 6 or RAID 10. So I would encourage you to, look up how RAID 6 and RAID 10 work and see how it differs from what we have discussed here. Okay, but just to give you some idea, when you go when you increase make the failure model more complex. So when you go from a single disk to two disk failure, for example, the complexity of the system increases exponentially. So in general, for any fault tolerant system design, not just for disks, if you go from a single component failure to say 2-component failure or 3 or 4-component failure, the number of states of the system that you have to handle increases exponentially, and that likewise it becomes much harder to provide those performance guarantees. So so that's one of the big challenges. Even going from 1 to 2 disks makes the system incredibly complex. So keep that in mind. But you can also do this thought exercise. How would you go about solving a 2-disk reliability problem, like where you don't want to lose any combination of 2 disks? Okay. All right. And finally, there's a bullet point here which says that people often use NVRAM to improve write performance. What that means is that you would write to when you do a write operation, and let's say you suddenly lose power, then writes are temporarily committed to the NVRAM, and then either you may have a battery backup, or when you later power on the system, then the writes can be committed to the disk. Also, NVRAM provides you a bit of reduces some of the latency required to go onto the magnetic disks to commit the write to magnetic disks. Okay, so yeah, so Shenglong has a comment that 2-disk failure would be RAID 6, and that's right. But how would it work? That you have to. That's kind of a homework, not part of the official homework, but curiosity homework that you can find out. And even before go and read about RAID 6, just think about it. How would you do it? Okay, and see whether you match what they actually do in RAID 6. Okay, that will give you some idea of the difficulty of achieving this. Okay.